Hi, everybody. So today I want to talk about aromatic substitution, and I hope to give you a little table that collects a lot of the stuff that we need to know about aromatic substitution in one convenient place. Okay, so what's going on in the lecture now is a whole lot of talk about aromatic substitution. So let's just briefly review the mechanism and what exactly this reaction accomplishes. Aromatic substitution. All right, so we have a benzene ring, and this is the nucleophile. And we're studying a bunch of reactions that are going to replace a ring hydrogen of the benzene ring with an electrophile. So I'm going to put a hydrogen there, and then we have the reaction of the benzene ring with an electrophile. This is the electrophile. And so that E plus, that's all very generic. But what would be some concrete examples of the electrophile that we would see? Well, there would be lots of them. So we could have X plus. So this could be Br plus or Cl plus typically. Or we could have maybe something that kind of looks like a carbocation. That's another electrophile that we see. We could have the nitronium ion with positive charge on the nitrogen, or we could have an acylium ion, maybe something like that. So we study a bunch of reactions, and each of those reactions produces a different electrophile, which is then snapped up by benzene, which functions as the nucleophile. Okay, and so what happens in this reaction is that one of the pi bonds of benzene, that's the nucleophile, it attacks the electrophile. The electrophile ends up attached to the benzene ring, and we get this intermediate, which is called a cyclohexadienyl cation. So what I've written here is one of the resonance forms of this intermediate. There will always be at least 3 resonance forms that describe this intermediate, but in some of these reactions, depending on the structure of the benzene ring here, of the aromatic ring, you get more. So let's just take a little bit of time to write out the other resonance forms. So as I said, there's always a minimum of 3. So we would have another resonance form where we could push that double bond. And so there's another resonance form, and then we have a third resonance form where we're pushing that double bond, and we come out with that. Okay, so there are the 3 resonance forms. As I said, there's a minimum of 3, but sometimes there are more. All right, so before leaving this intermediate, I have a few comments to make about it. First of all, this step of aromatic substitution, this is the slow step, because what you're asking benzene to do is to give up its aromatic stabilization. This is not benzene. This is not aromatic. This is non-aromatic, right? Because we talked about how to be aromatic, you need a planar cyclic array of p orbitals having 4n plus 2 electrons in that planar cyclic array. Well, this is not a planar cyclic array here. It's a horseshoe. You have a p orbital there, p orbital there, 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 there. You have a horseshoe of p orbitals. You're looking for a donut. right? You're looking for a donut, no donut there. So this reaction, this step of the reaction mechanism is slow because you're asking benzene to relinquish all of those 130 or so kilojoules of aromatic stabilization. Okay, so that's the first step. Another thing I'd like to point out about these resonance structures is that look where the positive charge is. Positive charge to the left of where the electrophile comes in, positive charge to the right of where the electrophile comes in, and positive charge on the ring carbon diametrically opposed to where the electrophile came in. So this is a pattern that we see repeatedly. We get a minimum of 3 resonance structures with positive charge left, right, and across. Okay, so now the next step and final step of this reaction mechanism, generically, is going to be a very fast, because in this step, benzene is recapturing its aromatic stabilization. So the ring undergoes a deprotonation, and we have that benzene ring with all of its aromatic stabilization back again. This step is very fast because benzene is recapturing its aromatic stabilization. And if we wanted to draw an energy diagram for the reaction, what we would see is a big, huge hill like this up to that intermediate, and then a tiny little hill down to the front. So this is where benzene and the electrophile live. This is the cyclohexadienyl cation. That's where he lives, right? But this is a big, big, huge hill because benzene has lost its aromatic stabilization. And here we have the product. Sorry, everything got kind of squunched up here. So what has happened is that a ring hydrogen is replaced by the electrophile. And all of the various reactions that we study about aromatic substitution are ways of generating this electrophile. Okay, so what you're going to do is the electrophile magically appears on the benzene ring, and a ring hydrogen is replaced. That's substitution. So just want to talk more about the generalities of this reaction, but let's just look at one concrete example. So if we start out with benzene, react that with bromine, molecular bromine, in the presence of iron trichloride catalyst. So this is a way of generating, and I'll put this in quotes, this is a way of generating the electrophile Br+. And so what's going to happen is that one of the ring hydrogens of benzene is going to be replaced, and we're going to have bromine magically pop up on that benzene ring, right? So what would this be good for? Well, now we've halogenated benzene. We can do maybe a Grignard, we could do maybe a Grignard reaction using this as the source of the halide, or, you know, this has other consequences that we can see in synthesis. All right, so I want to work with this reaction, bromine, molecular bromine, FeBr3. This is a way of putting Br on the benzene ring. So this is very simple. This is very entry level. All we've done is replace one ring hydrogen with bromine, but now let's start complicating matters. And the two complications are that of regiochemistry and that of relative reaction rate. So that's mostly what I want to talk about. All right, so for example, instead of starting with plain old benzene, what if we were to start out with methoxybenzene or anisole? And if we were to react that with bromine in the presence of FeBr3, bromine is going to replace one of these ring hydrogens. But now we have options. We have regiochemical options. So that bromine could go on the position next to the methoxy, or it could go on the ring position once removed from the methoxy, or it could go on the ring position diametrically opposed to where the methoxy was. So introducing this methoxy substituent has now opened up the possibility of having 3 different bromination products. So this one, 1, 2, the pre-existing substituent is at 1, the incoming electrophile is at 2. I could call this one 1, 2, but the usual terminology here is to call this the ortho substitution product. Ortho from a Greek word meaning straight. For example, remove all orthodontia before kissing. You go to an orthodontist, what does the orthodontist do? Straighten your teeth. So this means, from a Greek word meaning straight. This guy we could call 1, 3, where the pre-existing methoxy substituent is at carbon 1 and the new electrophile is at 3, but this is not real. The conventional terminology here is that this is called the meta substitution product, from a Greek word meaning after. I guess it means after the ortho. This guy we could call 1, 4, but it's conventionally called the para substitution product. All right, and ortho, meta, and para, this all takes a whole lot of time to write. So lots of times we just abbreviate that with an O. We just abbreviate that with an N. We just abbreviate that with a P. So what we want to understand, what we want to understand is that when this reaction happens, well, it turns out that we get 100% yield of this thing and 0% yield of that and 0% yield of that. We would like to understand why. Okay, so this ortho, meta, and para terminology, that's important. So let me give you a problem. What would we call that? Paradise. No? Okay, not fine. What about that? What would we call this guy? Orthodox. Orthodox. MD, you pre-meds out there? Okay. All right, so I'm going to give you a little table now. Well, actually not little, it's quite extensive. And so what I'm trying to do is collect everything that we need to know about regiochemistry and about relative rate in one convenient little package. The most important thing to focus on is what is the atom directly bonded to the benzene ring in the pre-existing substituent. How could we characterize the atom directly bonded to the benzene ring? That is the key. If the substituent directly bonded to the benzene ring, and I'm just going to call it Z, if the substituent directly bonded to the benzene ring has an unshared pair of electrons on it, this is going to be an ortho-para director.
In other words, it's going to steer the incoming electrophile to the ortho position and to the para position. Now, because this group can be big, right? We just saw methoxy. This group can be big. Most of the time, when you're dealing with an ortho-para director, the major product will be the para substitution product for steric reasons. So if the atom directly bonded to the benzene ring has an unshared pair of electrons on it, the new substituent, the electrophile, will be steered to the ortho position and to the para position. But for steric reasons, the major product in this situation will be the para substitution product, where the electrophile is coming in far away from that pre-existing substituent, which may be big and bulky, and screen the nearby ortho positions. Okay, so that's the regiochemistry. Now, something like this, in aromatic substitution, the benzene ring is the nucleophile. The best nucleophiles are the most electron-rich nucleophiles, so that if the atom directly bonded to the benzene ring has an unshared pair of electrons on it, this electron pair can be donated to the benzene ring, and that makes the benzene ring more nucleophilic, more reactive, so that when the atom directly bonded to the benzene ring has an unshared pair of electrons on it, not only is it an ortho-para director, it is also a strong activator, meaning it's very reactive. Sure it is. In aromatic substitution, the benzene ring is the nucleophile, and this atom can kick electrons into the benzene ring, making it more reactive. And so we call these kinds of substituents strong activators. But the truth is so messy. So I'm going to have to put a little star on that. And there is an important exception that we encounter very, very frequently. Get to that later. The all-important thing is, what is the atom directly bonded to the benzene ring doing? How can we categorize it? If the atom directly bonded to the benzene ring is part of a carbon-carbon double bond or a carbon-carbon triple bond, this is also an ortho-para director. But because these groups don't have an unshared pair of electrons to kick in, these are now considered weak activators. They're not as reactive as this group up here, but they are still pretty reactive. Okay, so those are the weak activators. If the atom directly bonded to the benzene ring is sp3 hybridized, that's also going to be an ortho-para director. That is also going to be a weak activator. So this whole conglomeration of stuff, that fits into our next little category, right? We're focusing on what the atom directly bonded to the benzene ring is doing. Is it part of does it have an unshared pair of electrons on it? Is it a part of a carbon-carbon multiple bond, or is it an sp3 hybridized carbon? But yet again, the truth is so messy. So I'm going to have to put a little star, 2 stars on n, because there are some exceptions. Okay, so now we can get to one of these exceptions, and that is if the atom directly bonded to the benzene ring is a halogen. And remember, we always use X to represent a halogen, so this could be F, Cl, Br, or I. If the atom directly bonded to the benzene ring is a halogen, it fits into this category in that it's an ortho-para director, but because halogen is highly electronegative, and because in aromatic substitution, benzene is the nucleophile, and this guy is sucking electrons away from benzene. This reduces the reactivity of that benzene ring. So if the atom directly bonded to the benzene ring is a halogen, it's going to be an ortho-para director, but now it's going to be called a weak deactivator. It slows the reaction down because the highly electronegative halogen is sucking electrons away from benzene. And in aromatic substitution, the benzene ring is the nucleophile. So that's our next little category here. Okay, now we're looking at the atom directly bonded to the benzene ring. And is that atom part of a multiple bond, a carbon, but this is part of a multiple bond, but not a carbon-carbon multiple bond. So that's what I'm trying to express here. This could be a carbon-oxygen double bond, or this could be a nitrogen-oxygen double bond, or this could be a carbon-nitrogen triple bond, just not another carbon-carbon multiple bond. This is some other kind of multiple bond that doesn't involve two carbons. Well, when the atom directly bonded to the benzene ring is part of a multiple bond, but not a carbon-carbon multiple bond, some other kind of multiple bond, these are meta-directors. They're going to steer the substituent to a meta position, and because now resonance, we can draw resonance structures that take electrons away from benzene, these kinds of substituents are strong deactivators. They really reduce the rate at which benzene reacts. They're not kicking electrons into benzene anymore. They're taking electrons away. If this is a carbon-oxygen bond, carbon-oxygen double bond, or this is, say, a carbon-nitrogen triple bond, they are taking electrons out of benzene by resonance. Okay. Last little category here. If the atom directly bonded to the benzene ring has a full positive charge or a substantial partial positive charge, these will be meta-directors and they will be strong deactivators. Okay, and so now we can look at this exception over here. The carbon, the trifluoromethyl group, right? That's a carbon atom. It's sp3 hybridized. It looks like it should fit in here, but it is not an ortho-para director. It's a meta-director because you've loaded this carbon up with all of this highly electronegative fluorine. This carbon atom has a pretty good partial positive charge on it as a result of inductive withdrawal of electrons by the fluorine. So there are other exceptions. The CCl3 group is also a strongly deactivating meta-director. There are a few exceptions, but this is really the one that we encounter most of the time. Okay, now before leaving this table, I don't know if we're going to have time to talk about this today. May have to wait for this for another time. But the strong activators, they are called class 1. Strong activators are class 1. This doesn't have too much meaning now. I don't think I'll be able to get to it, but I just want to put on the record. Weak deactivators are class 2. Weak activators and weak deactivators are called class 2. And then the strong deactivators, this is class 3. All right, what these classes have to do with anything, we'll talk about that able to. Okay, so we're going to leave this table up. This doesn't explain really why anything is the way it is. It's just a summary of experimental results. Okay, so now let's do some problems where we're utilizing the information here on this table. Okay, predict the product. So it's an aromatic substitution. Remember this BR2 and FeBr3, what do? They put Br on the benzene ring. The question is where? So what about the NO2 group, right? So what do? You look at the atom directly bonded to the benzene ring. That is going to tell you whether the major product is going to be ortho, meta, or para. And you look at the atom directly bonded to the benzene ring, that's going to allow you to say something about whether the reaction will be fast or slow. So what about the nitro group? Is that an ortho-para or a meta-direct? That is a meta-direct, because when you explode the nitro group in all its glory, and you write out the Lewis structure of the nitro group, and if you can't do this, you're sunk. The atom directly bonded to the benzene ring is part of a multiple bond, but not a carbon-carbon multiple bond. This is a carbon-oxygen multiple bond. That puts it in this category, meta-directing, strong deactivator, class 3. Look at the atom directly bonded to the benzene ring. It has a positive charge on it. That makes it a meta-director, strong deactivator, and class 3. So nitro is a meta-director. So the major product would be this meta-substitution product. Okay, so you see how you use this table? See how you use the information on this table? Okay, let's try another one. What about I'm just going to put those ditto marks, meaning we're just going to brominate everything. That's the only reaction we're going to talk about. Because we're not talking about individual reactions, we're talking about regiochemistry and relative rate of reactivity. So what about this acetamido group? Is that an ortho-para or a meta-director? And will this reaction be fast or slow? So what do you think? Acetamido, ortho-para or meta-directing? Oh, the key is to look at the atom directly bonded to the benzene ring, which is this nitrogen atom. And this nitrogen atom has an unshared pair of electrons on it, right? That puts it into this category. And is nitrogen a halogen? No. So it's not in here, right? It's an ortho-para, strong activator, class 1. So this guy is steering the new BR to the ortho positions and to the para positions. But because the ortho positions are screened sterically by the pre-existing substituent, when you're dealing with an ortho-para director, the major product is nearly always going to be the para substitution product for steric reasons. So the product here is the major product is going to be the para substitution product. So something like that. Okay, let's see, let's try another one. What about something like that? What would be the major product here? CN. Look at the atom directly bonded to the benzene ring. It fits into one of these categories. That's how we can predict whether it's going to be an ortho-para or a meta-director. So CN, if I were to write that in all its glory, what I would be writing is a carbon-nitrogen triple bond there. Nope, nope, it's not a carbon-carbon triple bond, it's a carbon-nitrogen triple bond. That's in this category. It's a meta-directing strong deactivator class 3. So the major product here is going to be the meta substitution product. And clearly, if, since what I'm suggesting to you is you look at the atom directly bonded to the benzene ring, if you don't know how the CN group is put together, you're sunk.
Professor Rubio, I have a question.
Yes.
Oh, you say it's ortho para, for example, for like class 1, but like would it always be more para than ortho?
Yeah, for steric reasons, it's always going to be more para, except with the methyl group. The methyl is an ortho-para director, but because it's small, the major product there is the ortho substitution product. But see, this substituent, that's huge. It's screening the ortho groups, the ortho positions.
Okay. Okay.
Did that explain anything?
Yes. Thank you.
Sorry, I have a question too.
Okay.
So if it's a CC triple bond, does that end up with an ortho or a para?
That's going to usually be a para substitution product, but that's another case. The triple bond is compact. It's like a little pencil. It doesn't screen the ortho positions that much.
Okay.
So, but it's usually para.
Okay, thank you.
So, let's see, before we get to the next group of problems, let me ask you this. Okay, so let's say this is an ortho-para director. And let's say we brominate this.
Statistically, how much ortho substitution product would we get? Statistically, how much para substitution product should we get? If the ortho positions and the para positions were exactly this equally reactive, and if the size of this group had nothing to do with anything, we would get 67% ortho and 33% para, right? Because there are twice as many ortho positions as there are para positions. So that if the size of this group had nothing to do with anything, you would get more ortho product than you would para product on statistical basis. But we never observe that except when this substituent is small, like a methyl group. For methyl, we get about 66%. We get about this distribution. But that's an exception. Most of the time, the para position is going to be the site of major substitution because the size of this Z group matters. Oh, okay.
Professor Rubio, I also have a quick question.
Okay.
Also, if it's a deactivator, I know you were mentioning like how fast it goes. Would it be a slower reaction if it's a strong deactivator?
It would.
Okay. Thank you.
The strong deactivators react something like 25 orders of magnitude, not 25 times, 25 orders of magnitude more slowly than this. In a laboratory, if you have one of these strong activators, you add the electrophile, boom, 100% yield instantly. But with these guys, you're going to have to heat it for hours maybe. So there's a big difference.
Thank you.
Okay, let's see. Now let's talk about, let's talk about the, since we know about whether to send something ortho and para, let's talk about activation and deactivation before we run out of time. Okay, so here's our next level of complexity. We know what's going to happen. Br is going to go somewhere on one of these benzene rings, but now we see two benzene rings. So the crisis here is we know what's going to happen. Br is going to magically appear on the benzene ring. The question is on which ring and where. So why don't you try to figure that out, and then we will divulge the answer. So who's going to get the Br? The ring on the top or the ring on the bottom? Oh, it's the ring on the top is going to get the Br because the ring on the top has an activator on it, a strong activator. The atom directly bonded to the benzene ring has unshared pair of electrons on it. The ring on the bottom has a strong deactivator on it. So the ring on the top is more reactive than the ring on the bottom because the ring on the top has the activator on it. Okay, and so this is an ortho-para director. The para position is blocked. There's something already there. We can't put a Br here because then we'll have a carbon with 5 bonds. So this is an ortho-para director, but because the para position is blocked, the new substituent must go ortho to this methoxy group, steric hindrance or no steric hindrance. So the product here is going to be the product of ortho substitution. Okay, let's try another one. What about something like this? And once again, we're just dealing with bromination. What would be the product here? Once again, we have two benzene rings. We know what's going to happen. Br is going to go somewhere on the benzene rings. But the question is, which benzene ring is going to get it? And where on that benzene ring will the new Br appear? So are you thinking about that? Which ring's going to get it? The one on the left or the one on the right? Oh, it's going to be the one on the right because this guy here, the atom directly bonded to the benzene ring, is part of a multiple bond, but that's not a carbon-carbon multiple bond. This is a carbon-oxygen multiple bond. That's a meta-directing strong deactivator. This benzene ring, the atom directly bonded to it, has unshared pair of electrons on it. And is this halogen? No. So that this is a strong activator. One ring is deactivated, the other ring is activated. So the ring on the right is going to get the new Br. This is an ortho-para director. Most of the time, the major product is going to be the para substitution product. So we'll get, as the major product, we'll get this. Yes? So see how to use the information here on this table. Okay, next level of complexity is, so we started out with a single benzene ring with one substituent, and now we saw some examples of two benzene rings, and we're deciding which benzene ring is going to get it. How about now we look at a benzene ring that has more than one substituent on it? And how do we figure out what the major product there is going to be? Okay, so here's our next level of complexity. We have a benzene ring with more than one substituent. So where is the new Br going to go? Are you thinking about that? Are you guessing where's the new Br going to go? Okay, this is where our classes come in. Class 1, Class 2, and Class 3. So look at Br. That's Class 2. It's a orthopara-directing weak deactivator. That's Class 2. All right, now, what about nitro? Well, we had a problem earlier that showed that nitro fits in here, right? We exploded the Lewis structure. We see that nitro is a meta-directing strong deactivator. That's Class 3. So in the war between substituents, in the war between pre-existing substituents, the winner is the group that belongs to the more reactive class. In other words, Class 1 beats Class 2, Class 1 beats Class 3, Class 2 beats Class 3, and Class 3 doesn't beat anything. So here I have a weak deactivator versus a strong deactivator. Who is more activating? The Br is. So the Br has everything to say about where the new substituent will go. Br as an orthopara director, it is saying send the new substituent ortho to where I am and para to where I am. But as we just saw that whenever we're dealing with an orthopara director, most of the time, the para substitution product is the major product. So the major product here that we would predict would be one in which the new substituent was steered to the para position by the more activating Class 2 that beats a Class 3. Okay, so that's what these reactivity classes are for. When you have a benzene ring that has more than one substituent on it, it's the one in the more reactive class that decides.
Professor Rubio, I have a question.
Okay.
Let's say you had a similar example, but the weak deact was like more to form an ortho. On which side would the ortho form?
So are you talking about 1-bromo-4-nitrobenzene?
Yes.
Well, the two positions ortho to the bromine are equivalent, so wouldn't matter whether you send it to the left or the right.
Okay, it doesn't matter. Okay. Thank you.
Okay, so now the truth is so messy. Okay, so what is going to happen here? So we're using these reactivity classes to predict where the electrophile will go when we have a multiply substituted benzene, right? So here's a multiply substituted benzene. and we fit each of the pre-existing substituents into one of the three reactivity classes, and the more reactive class has everything to say about where the new substituent will go. So what reactivity class is methyl? That carbon is sp3 hybridized. It's an ortho-para-directing weak activator class 2. What about Cl? What group does it belong to? Well, that's this guy. He's an ortho-para-directing weak deactivator. Uh-oh, here's the crisis. Also class 2. Now, it would be nice. This is an activator, weak activator. This is a weak deactivator. It would be nice if this guy had everything to say about what happens next, but that is just not how it works. Because the weak activators are not that much more reactive than the weak deactivators. So one is an activator, one is a deactivator, but this guy, weak activator, is not really significantly more activating than a weak deactivator. So here, what I'm trying to say is that both substituents belong to the same class. They're both class 2. We would have the same issue if they were both class 1, or we would have the same issue if they were both class 3. They have an equal say in where the new substituent will go. So we're going to get a lot of this where the methyl is saying, send the new substituent ortho and para to where I am, but the para position is blocked, so this BR goes ortho. And we're also going to get a lot of this guy, where now the Cl has had its say, right? So when the two substituents are in the same reactivity class, they don't have exactly an equal say, but we're going to get a lot of both of these products. So this is not a good synthetic reaction, because when we run a reaction in the laboratory, we want a clear-cut major product. Here we're going to get a mixture of these two products. I don't care if this is activating, I don't care if this is deactivating. This guy is not orders of magnitude more activating than this one. And we would have the same issue if they were both class 1 or both class 3. Okay, so let's try some more. Okay, what would be the major product here? All right, so this is fast, but let me rewrite it this way. Okay, what would be the major product here? Which ring is going to get it? The one on the top or the one on the bottom? Symmetrical. It doesn't matter which ring gets it. It's going to be the one on the top or the one on the bottom. It doesn't matter. I'm going to give the BR to the ring on the bottom, just arbitrarily. All right, so this ring is going to get the BR. The atom directly bonded to the benzene ring that's going to take the electrophile is part of a carbon-carbon multiple bond. This is an ortho-para-directing weak activator. The ortho positions are screened. The major product will have the BR in this para position. Yes, so that's all understandable based on what we've done. Okay, now what if I were to take this and
feed it more BR2.
A second equivalent of BR2. Now what? Which ring's going to get it? The one on top or the one on the bottom? Is it going to be the one on top or the one on the bottom? It's going to be the ring on top. Because this guy, this ring on the bottom, has a weak deactivator and a weak activator. The ring on the bottom has a weak deactivator and a weak activator. So the ring on the bottom, its reactivity is pushed up by the activator, but then pushed down by the deactivator. The ring on the top doesn't have any deactivators on it. It just has this activating benzene ring, where the atom directly bonded to the ring on the top is part of a carbon-carbon multiple bond. So the ring on the top has an activator on it. The ring on the bottom has an activator and a deactivator on it. So the ring on the top wins because it doesn't have a deactivator. So the main product there will be that. Okay, now what if I were to take this and do it again? More Br2, more iron trichloride. Now what? 3 equivalents. Once again, the molecule is symmetrical, so that it doesn't matter if I brominate the ring on top or the ring on the bottom, they're equivalent by symmetry. So I'm going to give the new Br to the ring on the bottom. So the ring on the bottom has a class 2 down here, and this thing is also a class 2. So they belong to the same reactivity class. They have a very significant say of where the next substituent will go. So this benzene ring on top is saying send the new substituent ortho and para to where I am. You would get that. Whereas this guy, Br, is saying send the new substituent ortho and para to where I am. So you would start getting a pretty bad, pretty ugly mixture of products. So it's kind of like a tennis match, right? If I were to add bromine again, this ring has 2 deactivators on it. This ring only has 1 deactivator on it. If I were to add bromine again, the ring on the top would get the new bromine. So it's kind of like a tennis match, right? First one ring, then the other ring, then the other ring, then the other ring. They're like, the bromine is going back and forth. Okay. Any more questions? Because I'm about to quit. I have to go to my next Zoom. Well, that's all I have for you today. On Friday, on Friday, I think we'll have, talk a little bit more about aromatic substitution, although the lecture portion of the course will be over. See you then.
Thank you.
Okay, bye-bye, everybody.